Okay, this video is for a review of the Unit 3 exam question. So this is AP Chemistry Unit 3. I gave a 15 question exam on Unit 3, and here I am going over the answers. So this first question says, basically we're adding helium to a rigid container. So it says a rigid container holds 0.5 moles of argon and 3/4 of a mole of oxygen. How will the total pressure of the gases in the container and the partial pressure of oxygen be affected by the addition of 0.25 moles of helium at constant temperature? Both the total pressure and partial pressure of oxygen will remain constant. Both the total pressure and partial pressure of oxygen will increase. Okay, so in a rigid container, volume doesn't change, right? Because you have this container, it's rigid, so nothing can get in and nothing can get out, right? And the problem says the temperature stays constant, right? Constant temperature, if you look here. Constant temperature. Okay, and so the ideal gas relationship is basically with pressure, and so pressure is proportional to the, so I think that's a proportional sign is this, to the amount of, so N is the moles, right? Moles. So and moles is just the amount of something. So the pressure and the moles is what will kind of be dictating, how much the total pressure will be. So in the beginning, we start out with 1/2 mole of argon and 3/4 of a mole of oxygen. And then after adding the helium, here, after adding an additional 0.25 moles of helium, then it goes from basically 1.25 moles of everything in the container, and then it ends up with adding a 0.25, so it's 1.5 moles. And so the pressure has to go up, the total pressure, because there's more gas particles here now. There's just more, right? So think about it. If you were to have a bag or a water bottle and you blow more air into it, the pressure increases. But the oxygen partial pressure would not change, because the partial pressure for a specific gas in an ideal mixture, so there's an equation for this, and I think it was in your unit notes. It's that the pressure of oxygen, it would be the moles of oxygen, N, so let's put an O here, and then R, and then temperature over volume. And so nothing changes for oxygen, right? Because oxygen, it stays at 0.75 moles, right? So this doesn't change, so this stays the same. This stays the same. This is constant. This always stays the same. So all these are constant. And this stays the same too, because there's no additional volume. So this stays the same. This stays constant. So the total pressure will increase, but the partial pressure of O2 will remain constant is the answer. And so a lot of people think because the percentage of oxygen now is lower, so the pressure of oxygen will drop, and that's not true. The overall mole fraction of oxygen does decrease, but the total pressure in this rigid container increases, and so those effects they cancel, because the pressure of oxygen is dependent on the moles of oxygen. So that's why it's D. Okay, next question, number 2. Here, It talks about solid Al, so what is that? Aluminum nitrate is added to distilled water to produce a solution in which the concentration of nitrate, NO3 minus, is 0.1 moles. What is the concentration of aluminum ion Al3 plus in this solution? So we already know however much aluminum there is times 3 the nitrate. And so, so we know there's times 3. So if we figure out, how many moles, of NO3 there are, we know that there's 1/3 of the amount of aluminum. Well, they kind of give us NO3, right? NO3 is, so here we have this, NO3 is 0.1 moles. So I'm going to write here, NO3 is 0.1 moles. And because this is a 1-to-3 ratio, we can divide, not what I meant to do. Okay, well, great, I can divide this. So 0.1 moles divided by 3 equals 0.033 moles of aluminum. What you don't want to confuse, though, is assume that they're equal concentration, right? So there's, for every one molecule of this or atom of this, there's 3 molecules of the nitrate. So you don't want to mix that up. So the answer would be, I should put some space. I should have put some space in here. It's not MAL, it's moles of aluminum. So that is B. Okay, move along. We see this image here. What holds CCl4 molecules together in the solid? The attraction between, so sodium, solid carbon tetrachloride, CCl4, is represented in the diagram above. The attraction between the CCl4 molecules that hold the molecules together in the solid state are best identified as. So CCl4 is a solid molecule. That means the solid is made of whole CCl4 molecules. So we see that. We see that here. There's they're connected by, the carbon in the center and the 3 and the bonds between the 3 or 4. Here we see 1, 2, 3, 4 chlorines. So all of these seem to have 4 chlorines, right? So since it is CCl4, and they're not ions, and they're not a crazy big covalent network. So inside each of these, the CCl4 bonds are polar, because chlorine pulls electrons harder than carbon. So there's probably a this dipole moment here, right, where this is more electronegative and this is not as electronegative. But the molecule is symmetrical. It's tetrahedral. It's like 1, the carbon, like a pyramid, right? And so since the whole molecule is kind of equal, I think these are, correct me if I'm wrong, 109 degrees. Since they're all equal, all of these dipole moments cancel out. They all cancel out. And there is no permanent dipole. So, the main attraction between the molecules can't be dipole-dipole. So the attraction is that the electrons, they shift around randomly, creating temporary dipoles, which makes a dipole in a neighbor. And so they attract for a while. And I taught you guys this, and that should be temporary dipoles. So the answer should be C, because they create temporary dipoles, but not ones that stick around for long. Okay. Let's see question number 4. So this question, which of the following was the best piece of laboratory glassware for preparing 500 milliliters of an aqueous solution of solid? So when you want an accurate final volume, you use a volumetric flask. It's calibrated, so the bottom of the meniscus hits the exact line when the volume is exactly 500 milliliters. Erlenmeyer flask, here, Erlenmeyer flask is more so for mixing. This is good for mixing. It's good for like swirling reactions. Not for precise volume. And beaker is not for any of this. Beaker is for like a rough idea. This is more for a rough idea. And then a graduated cylinder is good for measuring. Good for measuring. But it's not super accurate. So this is what you want. Okay, moving on. Next question. The 0.2 mole sample of MgCl2 in solid and a 0.10 mole of KCl are dissolved in water and diluted to 500 milliliters. What is the concentration of chlorine in this solution? Okay, so you have, the most important information here is you have 0.2 moles of MgCl2 and 0.10 moles of KCl. And so, but your final volume, and after everything is put together, it's 500 milliliters. Okay, so what happens is MgCl2 breaks apart because it's a salt. And so the MgCl2 turns into Mg2 plus in order to balance out these two Cl minuses and the two of the Cl minuses. So every 1 mole of this will give you 2 moles of the chlorine. So if they're telling us 0.2 moles of this, 0.2 moles of this, it'll be 0.4 moles. So there's twice as many of them, right? Because moles is just a quantity of the 2Cl. And the KCl gives us K and Cl, so it's a 1-to-1 mole. So K plus, and remember Cl is always negative, Cl minus, and that gives you a 0.1 mole and a 0.1 mole. Right, and now if you take this, the 2 Cl's here, and you add them together, you get 0.5 moles of Cl minus. And that's B. Don't worry, I'll upload this onto Schoology as well. Oh, wait. But we didn't divide. So we have 0.5 moles. So actually, that's wrong. So we have 0.5 moles of Cl, but we also, the last piece of information, we have half a milliliter. Oh, I almost made a classic mistake. You got to divide this by 0.5 liters. I almost left it in, look, they gave us this, and I almost left it in, I didn't change it to molarity. Okay, so 0.5 liters, because, that's how much 500 milliliters is, 0.5 liters, and that gives us 1 molarity. So the answer would not be C, the answer would be D. Because the 0.5 and the 0.5 would cancel out and give you 1. Almost made a mistake there myself. Okay, question number 6. A student uses visible spectrometry to determine the concentration of COCl2 in a sample solution. First, the student prepares a set of COCl2 solutions of a known concentration. The student uses a spectrophotometer to determine the absorbance of each of the standard solutions in a wavelength of 510 nanometers and constructs a standard curve. Finally, the student determines the absorbance of the sample of unknown concentration. Okay, the original solution used to make the solutions for the standard curve was prepared by dissolving 2.6 grams of COCl2, molar mass of 130 grams per mole, in enough water to make 100 milliliters of a solution. What is the molar concentration of the solution? Okay, so they're looking for the molarity. So first I turn the grams into moles using molar mass. Okay, so they gave a molar mass of 130 grams per mole. So here they tell us the molar mass is 130 grams per mole. So we're looking for the moles of COCl2. And that is 2.6 grams divided by 130, which they gave us, grams per mole. Okay, and that ends up being, if you do the math, 2.6, there should be a period here, divided by 130 will give you 0.02 moles, because the grams also cross out moles. Okay, but now we got to convert the grams, the moles to liters, and then moles per liters, okay? So now they give us 100, and enough to make 100 milliliters of solution. So 100 milliliters is equal to, now, if you could just divide this. This is kind of easy. Milli means 1,000, right? And you would lose this. And 1,000, 100 over 1,000 is 0.1. So it's 0.1 liters. And now you just divide to find the molarity. So molarity is, molar concentration is 0.02 divided by 0.1. And since you're dividing by 1/10, you're really multiplying. So this just moves over one place. So that equals 0.2 molar concentration. Okay, next question. Okay, let's take a look at this. I think I did this one in class. So you're looking at these three different molecules. They all have similar molar mass. Okay. And they're asking which one has the highest boiling point. I swear I did this one in class. So all three of them have similar molar masses, anywhere from like 72 to 74 grams per mole. So their boiling points are not going to be decided by mass. It's going to be decided by, other intermolecular forces. So boiling point is dependent on how strongly molecules can stick together. So pentane is nonpolar, right? Because it's nonpolar. There's no polarity here. There's no dipole moment here. So it can only have London dispersion forces. The butanol, which is 70, here, let me make sure I'm going to be able to write. So the butanol is polar, right, because of that oxygen. That electronegativity, there will be that polarity. So it has both. It has both dipole moments, and it has London dispersion forces. And then propanoic acid has a carboxylic acid group which can form hydrogen bonds. There's hydrogen bonding here. Because this COOH can form hydrogen bonds. So the strongest of these three, you should know, is hydrogen bonding. So the propanoic acid, it would be the hardest to break and to separate. So it would be the highest temperature you would need to boil. So let's see what the answer choices are. There's only one with propanoic acid because it can form intermolecular hydrogen bonds. Hydrogen bonds. It's the most important intermolecular force. It's the strongest, I should say, intermolecular force. Okay. So this question, you're taking 200 milliliters of 0.6 molarity, molar concentration of MgCl2. So it makes sense it's in water. That makes sense because aqueous means it's mixed with water, right? And what is the concentration of Mg in a resulting solution? Assumes volumes are additive. So here you would, so you start out with the fact that you have 0.6 moles of MgCl2 and 200 milliliters of, what did they say, 0.6 molar concentration. No, it's you have 200 milliliters of it. So you have 200 milliliters of this. I don't need to write it again. All right. And so since you have the moles of MgCl2, and so the moles, it's a 1-to-1 ratio, so you know your moles is equal to your molarity times your volume. And so what you do is, in order to get the moles, you take your moles, which is 0.6, and you multiply that by 0.2 liters, because you have a fifth of a liter, so 0.2 liters. And you multiply those two together, and you get 12, or you get 0.12 moles. That's how much, right? Moles. Right? So if you multiply molarity by the volume, which is this is the volume and this is the molar concentration, you will get how many of something you have. You will have the quantity. Right? Okay. And then now you need the total volume. Now your new total volume, they tell you, there's only two figures here. There's a 200 and a 400. And if you combine them together, so I'm going to do it in liters, 0.2 plus 0.4 equals 0.6 liters. Right? So that's 0.6 liters. So that's important. And this many moles, that's important. And what are they asking for? They're asking for the new concentration. Now, that's easy. So we just got to divide. We got to divide how much of the MgCl2 we have, which is 0.12 moles of the MgCl2 divided by 0.6. And if I calculate this correctly, 0.12 divided by 0.6 is a fifth, I believe. A fifth, or this is a fifth, right? This is a fifth. So the molar concentration in the new solution would be 1/5 or 0.2 moles. Next question. Okay, we're flying right through this. The molarity, what is the molarity of I minus in a solution that has 34 grams of SRI2 molar mass in 1 liter of solution? So this is probably the easiest question so far. So you have, first you want to figure out how many moles you have. So you have 34 grams, right? So you put 34 grams. Where'd it go? So you have 34 grams. And you divide it by however many grams per mole. And then the grams divide. And so here you have the molar mass, which is grams per mole, right? So that's 341 grams per mole. So that equals about 10%, right? So 0.10, I'm just going to round, 0.10 moles, because the grams got crossed out. And then, so for the iodide, we also need to calculate that. So for the iodide molecules, it's a SRI2, right? So for every SR, this is for the SR, but for the iodide, you double it, because for every SR you have 2 iodide. So you have 0.2 moles of the iodide. Okay, and so now they tell us we have 0.2 moles of the iodide. What are they asking us for here? What is the molarity? So we just divide by however many liters that there are. And so here they tell us 1 liter. So you have 0.2 moles of the iodine divided by how much solution there is, which is 1 liter. And so you get 0.2 molar concentration, molarity. And that's T. Okay. A student prepared, let's see what they prepared. 4 solutions of known copper and measured the absorbance of each solution using the same cuvette. The graph shows the data for two absorbance measurements done for each solution. Which of the following identifies the most likely error that affected the absorbance recorded for the solution with Cu, the copper, which is approximately equal to this. What is the graph telling you? Most of the points here look like a straight line, which matches Beer's law that as the concentration increases, absorbance should also increase proportionately. But in the second trial, you notice that there's something that goes wrong with those white boxes. So the point near 7 times 10 to the, so here, about here, this point right here is the one in question the most, right? It's too high compared to where it should have been, right? So I'm saying it's B. Because a fingerprint left outside the cuvette, it smudges it. So there's less light that goes through. Because remember, this absorbance, light needs to be absorbed, right? So it's a light, right? So it has to be absorbed. So the less light that makes it through the detector, the spectrophotometer interprets it as, it absorbed more light. So it just, it says that it's a higher absorbance. But the concentration actually didn't change, but because there's a finger smudge, so that's why I would pick B. This is a tricky question. I will say this is a very tricky question. Okay. So 3 equimolar gas samples are at the conditions given at the following table. Assume that the gases behave ideally. We have F2, N2, O2. We have their volume, pressure, and temperature. Which gas, if any, has the greatest density? All as F2, N2, O2. Okay, so here we have density, which is, how do you calculate density? Which is pressure times molarity over R times T. So for all three, they have the same temperature, so you can, and the same constant. So you can kind of like ignore these, right? Because it's the same. But really, this will tell you the density then, right? The pressure and the molarity, right? And so molarity is just how much you have divided by the total liters. So for calculating A, you have 2 for the pressure. You have pressure of 4 for a nitrogen, and you have a pressure of 5 for oxygen. And then so all the temperatures again are the same, so we can ignore this.
Okay, so for the M values, for conditions, which would have the greatest density. Two moles of each. And so here, okay, we could calculate the molar masses because F is 19 mass times 2 is 38. N is 14 mass times 2 is 28. And oxygen is 16 times 2 is 32, right? So all we got to do is multiply their pressure by this number, their molarity. And so when we do that, here we get 38 times 2 is 76. We get 28 times 4 is 112. And we get O2, which is 5 times 32 is 160. Is the biggest number here is O2. So, okay, yeah, I figured. Okay. Okay, let's look at question number 12. Okay, it looks similar. Okay, here, I think it's the same formula for density. Density equals P times M over R over T. And then here in this case, all the temperatures are the same, R times T, and you can ignore that. And so here, the pressures are 2, 4, and 2. So A, B, and C is 2, 4, and 2. And now we need the molar mass. Oh, here we can just multiply. 16 times 2 is 32. 30 times 4 is 120. 58 times 2 is 116. And again, the biggest one here is 120. So the greatest is B. Moving on. Okay, the table below shows the information showing 4 samples of gas at 273 Kelvin. The samples are in 4 identical rigid containers numbered 1 through 4. So all containers have the same volume. They all have the same temperature as well at 273 K. So that means what really matters here is the moles is going to be proportional to the pressure. The higher the pressure means the more moles. So the molar mass of SO2 would be 64.1 divided by 64.1, because that's the grams that we have, right, divided by the grams per mole. And we get 1. So finding moles in container 3, we would do something similar in that we would take 1 mole, right, 1 mole times 2, which is the pressure, divided by 1.96. And we get approximately 1.02 moles. And then container 3 has 16 grams. Oh wait, this was up here. And then container 3, we have 16 grams divided by 1.02. And that gives us about, it's the same, it's 15.7 grams per mole. And a molar mass of 16 grams per mole catches the methane. And so this is the 12 plus 4 mass, right, equals 16. So that's A. Okay. And last 2 questions. Okay, let's take a look at this one. A student wishes to prepare 2 liters of 0.1 molar KiO3. Proper procedure is to weigh out. So first you want to find molarity. So N equals M times V. And in this case, they give us 0.1 times 2. And that gives us 0.2 moles. And then you convert that into grams. So you multiply N times MV. We already have MV, remember. Equals 0.2 times 214 grams per mole. And that gives you 42.8 grams. And lastly, we need this many grams, right? So off the bat, we can take out C. And so what you need to do then is you need to dissolve it, right? And so you dissolve the 42.8 grams, and then you add water until it is up to 2 liters. And the only answer that says that is B. Last question. Which of the following is least soluble in water? And that's this one, because like dissolves like. So water is polar, and things that are polar will dissolve it. This has no polarity. Look, it all gets canceled out, because right, it's like this. It's all of its dipole moments get canceled out. You see, so it has no polarity, and water is polar, so it would dissolve things that are polar, like these. There's a dipole moment in all of the other ones.